Okay, so yes, I'll have I guess our last homework assignment will be related to what I will cover today, which will be what I think is an interesting. I always think something interesting. Interesting application of the Gibbs sampler. Okay, so the Gibbs sampler is useful when we want to try to draw from a highly multivariate distribution. Okay, and it's especially useful when we have a hierarchical model. Okay. And so the application that I will look at, the application of a Gibbs sampler will be document clustering, okay? Document clustering. So this is different from document classification, okay? Document classification, you have document classes. Like you might say, like this is an article about science, and this is an article about politics, and this is an article about health or something. I don't know, okay? And in that case, you have these classes already defined, and you're going to say if it's about politics, we would expect to see phrases like president and White House and Congress and representative and stuff like that, and those would have high probabilities. And if it's a document about health, you might see things like nutrition and heart and study and blah blah blah. I don't know, okay? Medication, things like that. And we could just take a document, split it up by words, and say like how many times did this word appear and how many times did this word appear, and then classify it that way. Document clustering is a lot more complicated in that you don't have classes already defined, okay? And so you just have kind of a pile of documents, and you would kind of read through these, and then you as a person, if you were given this task, you would have to say like, all right, these documents kind of go together, these documents kind of go together, these documents kind of go together, okay? So there's not predefined classes, and so it's a bit more more complicated than document classification, okay? Document clustering, so I'm going to just write, do not mix up document classification, where classes are already defined, okay? So here we're going to just say there are documents no defined classes, and we want to cluster them. Okay. Now, when we do document clustering, we're going to have to pick how many clusters to search for. Okay, so we will have to kind of define how many clusters we should produce. Okay, we want to cluster them, and we do need to specify how many clusters to look for. Okay, and so the idea here is perhaps I'm going to try to cluster them. Maybe I will search, we're going to split documents into two clusters, okay? So we don't even know how these clusters should be defined, but we're going to read through and we're going to say, okay, these ones kind of feel like they should go in this cluster, and these ones will go into this cluster, okay? Now we can loosely define them, but let's say, so just our example. We will search for 2 clusters, okay? And this will just keep a little bit of one portion of the math easier, okay? Because if you have 2 clusters, then you can use kind of a Bernoulli thing, and it's either going to be cluster A with probability P or cluster B with probability 1 minus P. So that keeps it easy. We can easily go into a multi-cluster thing by generalizing from the Bernoulli to the Dirichlet. And maybe you are or are not familiar with the Dirichlet distribution, and we will have to cover the Dirichlet distribution anyway, so I'll explain that shortly, okay? But just a little bit of notation. We're going to, I'm going to start with this. This is going to be the corpus, okay? And this is going to be all the documents that we have. Okay. Now, when I use the word document, it's very loose, okay? For example, a single tweet could be considered a document, okay? A document is basically just more than one word. I mean, I guess technically it could be just one word, okay? But a document is going to be, is basically a thing with a bunch of words in it, okay? And we're going to kind of keep things simple, and we're going to use what's called the bag of words model because it's easy. It's easier to deal with that. You know, there's problems with the bag of words model, but you know, models are just meant to kind of simplify our lives, right? Okay, so anyway, this big C is going to be the corpus. That's going to be all the documents we have, and I'm going to have big C 0. And this will be documents labeled 0, okay? And big C1 will be all the documents labeled 1. Okay? And then just little c0 will be the count of documents in the corpus 0, okay? Or basically a number of documents with 0, and little c1 will be the number of documents labeled 1, right? Okay, and again, we're going to use the bag of words model. Okay, and which basically says the order of the words in a document does not matter, okay? Okay, we treat each document as a bunch of words and their frequencies. Okay. So, you know, so the issues with the bag of words model would be that the sentence "I'm not happy, I'm upset" will have the exact same representation as "I'm not upset, I'm happy." Okay, because both of them have the exact same words and same count, but obviously those sentences mean very different things because in English, the order, the arrangement of the words and where that modifier not goes is very important, okay? As far as bag of words go, that is lost, okay? We're only going to kind of look at the words that appear, okay? So I'll just kind of write that. Problems. I'm not upset, I'm happy, versus okay. But, you know, it's, I would say the bag of words model is useful in situations where certain words kind of appear in only certain classes of documents, right? So if there are particular words strongly associated with a certain subject or certain cluster or whatever, then the bag of words model is useful in those cases. Strong links between words and subjects, clusters, topics, what have you, right? So for example, if a document contains the word horsepower, okay, right away you can imagine we're talking about cars, vehicles, engines of some kind, right? You know, so certain words, you know, really generally appear only in certain contexts and things like that. So okay, and so here's kind of the model that we're going to do. Okay, so we're going to have just kind of an extremely simplified document creation model. Okay, so first we're going to start with a Bernoulli trial. Okay, a Bernoulli trial with some parameter, I guess pi. All right, and basically, Bernoulli trial with some parameter pi, and this will decide if determine if the document is part of is class 0 or class 1. Okay, so it's like we flip a coin or something, some kind of thing, and it's either going to say the document we're going to generate comes from class 0 or class 1. Okay, and then so if class 0, okay, there's going to basically be a lexicon associated with class 0, okay? And then if class 1, we have a different lexicon associated with class 1, okay? So if you think of the, when you did the deciphering exercise, we had these lexicons that said like the word the should appear with this probability and the word house would appear with this probability, and things like that. Okay, so for example, you know, just okay, I don't know, maybe class 0. We're going to talk about, maybe this is about class 0 means the document's going to be about fruit, and class 1 means the document will be about sports. I don't know. Okay. And so if it were class 0, we might have, like, the word apple will appear with probability 0.10 and banana with probability 0.08. Okay. And let's say there's only 4 words in our entire vocabulary. Okay. And sports, we'll say ball and goal, or maybe points. Okay, this appears with much lower probabilities. Okay, and over here, if it's a document associated with sports, the probability for apple is going to be much lower, and the probability for banana is also much lower. I'm just making stuff up, where ball will be much higher, and point will also be much higher. Okay. Again, making these words up, and you can imagine just, you know, the entire lexicon that exists for the entire language, okay, or at least some subset of the language, maybe 100 words or 1,000 words or something, and you're going to say these are the kind of the key words that that we're dealing with, okay, and we're going to have different probabilities associated with each of these things, and basically if it's class 0, so we've got this lexicon going on here with more, and then from here we generate the document. With a multinomial distribution. Okay, and so did you guys cover the multinomial distribution? Okay, I'm getting blank stares. Okay, the multinomial distribution, and this will also be the same, generate document with the multinomial distribution. Okay, so I guess we'll take a detour and we'll talk about the multinomial distribution and the Dirichlet distribution, all right? Okay, so let's just do detour. All right, so first we have the binomial distribution, and basically the binomial, you're going to have n trials, and each trial has probability P of success, or I'm going to just call it class 1, and probability 1 minus P of failure, or class 2. Right? So that's what we have. I'm going to call this theta, actually. Probability theta of success and 1 minus theta of failure. Is that okay? So that's binomial. And then the, I guess the conjugate prior is the beta distribution. Okay? And the beta distribution produces a value of theta between 0 and 1, that we can use as the probability value theta in the binomial distribution. All right, so that should be review, right? So binomial, you either get a yes or a no. You get a yes with probability theta, and you get a no with probability 1 minus theta. Okay. The multinomial is the exact same thing as a binomial, all right, except you have more than two possibilities, okay? So rather than just a yes and a no, maybe you can get yes, no, maybe. Or you get red, rather than having heads or tails only, okay? So the binomial situations are like, I'm gonna flip the coin 10 times, and how many times will it land heads, okay? Rather than just heads or tails, now you have like a die that has 6 sides or something, okay? So the multinomial is a generalization of the binomial where we have more than just 2 possible classes, okay? Generalization of the binomial, okay? And we have more than 2 classes, okay? So, so rather you're going to have n trials, and then you have a vector of probabilities for each class. Okay, so let's say theta is going to be a vector, theta 1, theta 2, theta 3, theta 4 if we have 4 classes. Okay, where the sum of the theta i's will be 1. Okay. And the multinomial is basically going to be theta I to the x sub I, and then there's like a big factorial thing in the front. Okay, so now it's going to be something like if I roll the die, roll a 6-sided die 10 times, what's the probability that I get 1 1, 1 2, 0 3s, 1 4, 2 5s, I don't know, some exact outcome, okay? And that's what the multinomial distribution is. Does that kind of make sense? Okay, and then the conjugate prior for the multinomial. Okay, so this vector theta is basically a categorical distribution, right? So the vector theta is a categorical distribution showing how much each class should appear. Okay, all right, and then the conjugate prior of the multinomial is the Dirichlet distribution. All right. So what kind of values does the Dirichlet distribution produce? So the beta distribution will produce a single value theta that you can use in the binomial. Okay. And the Dirichlet distribution will produce a what? A vector theta that you can use in the multinomial. Okay, and so it depends. You've got all sorts of different Dirichlet things. Dirichlet that can produce vectors of length 4, vectors of length 50, vectors of length 1,000, okay, depending on how many classes you have in your multinomial distribution. So if you have a 6-sided die, your Dirichlet distribution will produce a vector theta of length 6, okay? If you have a corpus with 1,000 words, and each word has a different probability, but the sum of all those probabilities is 1, your Dirichlet distribution will produce a vector of length 1,000, okay? All with different probabilities that will add up to 1, okay? So the Dirichlet distribution will produce a vector theta that we can use in the multinomial distribution. Okay, the Dirichlet distribution will produce a vector theta that we can use in the multinomial distribution. Okay, and then, the length of theta depends on how many categories exist. How many categories exist in the multinomial distribution, or whatever it is. Okay. Yeah, and there's a lot of parallels between the Dirichlet and the beta distribution. So the beta distribution has 2 shape parameters. Okay. I think we call them alpha and beta, or A and B, or whatever it is. Okay, and basically, what is I think I talked about this, right? But what would a kind of a loose interpretation of what A and B represent? It's kind of, you can loosely think of it as like the number of successes. I don't know how I wrote successes here, okay? The number of successes that you've seen prior, okay? The number of successes in the prior, and the number of failures, I guess, we have seen prior. Right? So for example, beta 5,5 basically says we have seen 5 success and 5 failures. So I think theta is 0.5, okay, but other values are possible, okay? Whereas beta 5,000, 5,000, okay, would look like this, right? Okay. We have seen 5,000 success and 5,000 failures. Okay, so theta is very close to 0.5. Okay, it might be 0.499 or 0.501, okay, but it is almost certainly not you know 0.55 or something like that. Okay, so is that all right for the beta distribution? These numbers that we're using is kind of just how many times you've seen a particular outcome, all right? And you have two possible outcomes. You have a success and a failure. And so if you've got 5 and 5, you know, the value in the middle is quite close, right? Whereas, you know, beta 80, 20 says you've seen 80 successes and 20 failures. And so you're going to get something close to 0.8 being the peak there. Is that okay for the beta distribution? Okay, and so the Dirichlet distribution has, I guess, k shape parameters. I guess it uses a vector. Okay, I'll say the Dirichlet distribution uses a vector alpha of length k for its shape parameters. Okay, and k being how many categories you have. Okay, and then alpha sub k is going to be the kind of quote-unquote prior count of category K. Sometimes we might call this a pseudo count. So it's kind of the idea that, you know, we saw the coin land heads 5 times and tails 5 times, so we're going to use alpha as 5 and beta as 5. Here it's going to be like this, and so if we have so the vector A could be something like 15, 30, 15, 20, 4, and 50, or something like that, okay? And this basically means that category 5 didn't show up very often, but category 6 shows up very often. And so the resulting vector that gets produced by this will reflect this as well, okay? Okay, so a possible vector theta could be something like, theta could be, I don't know, how many total do I have? 130 observations? Okay, so, okay, so we're going to say like 0.1, 0.2, 0.11, 0.15, 0.0. I can't add this up. What is this? 4, 15, 30, 50, 60, 0.4 or something like that, right? So that's one possible vector, right? So possible vector theta is this, okay? And another possible vector theta produced by this Dirichlet would be this, and another one could be something similar, like 0.09, 0.22, 0.08, 0.16, 0.01, and, or maybe I'll do 0.02, Okay, I don't know what, and whatever else goes here, so it adds up to 1. Okay. What is that? 17, 39, 41, 57, 43. I don't know. Okay, something, right? Okay. But you know, this Dirichlet will not produce. I'll say should never produce. Does that kind of make sense? How what this Dirichlet is producing? It's so based on the kind of the prior counts or pseudo counts that we've put into alpha. These are kinds of the vectors theta that it might produce, but it should never produce a theta where it's like I'm going to just do 0.1, 0.1, 0.1, 0.1, and then this one will have like 0.5 and 0.1. Okay, this should never happen, right? Because according to the prior counts, the probability of category 5 should be very low. Okay, and for this to end up being 0.5, that kind of thing should never happen, right? Just like if the prior parameters for alpha and beta are like 80 and 20, okay, we expect most of the p's produced will be something around 0.8, maybe 0.75, 0.82, things like that. It should never produce a p that's 0.2 or something like that, okay? And similarly, you can define a Dirichlet distribution with kind of this vector of prior counts, and it's going to produce some kind of vector of probabilities that add up to 1, okay? And it's basically the categorical distribution for those things, but it should align with kind of the prior counts that we have seen. Okay, so that is that's the Dirichlet distribution. Okay, all right. So our document structure says we're going to basically flip a coin or something, a Bernoulli trial, and it's going to say it's going to be class 1 or class 2. Class 1 has this lexicon. It says these words have these probabilities, these words have these probabilities, and so on and so forth. And we generate a document, basically a bag of words, using that vector theta of word probabilities, and we use the multinomial distribution. Okay. If it ends up the other way, then we're going to get a different looking document, right? Because it's got different word probabilities. This one says apple and banana should show up very frequently, and so you're going to get a document with the word apple and banana showing up many times, okay? Whereas the document coming from the other thing will have very few instances of apple and banana, but lots of instances of ball and point, okay? And or play or whatever, you know, whatever words that should appear frequently if it's associated with sports or something. Okay, I'm going to draw the plate representation of our document generation, okay? Okay, so first we're going to have a these are the hyperparameters for the beta distribution. Okay? So these go into a beta distribution that produces some value pi. Okay, so, all right. And so this is the value pi that goes into a Bernoulli distribution. Okay, this Bernoulli Bernoulli determines if a document is in class 0 or class 1. Okay. All right, so the document, so now I've got a plate, and this is going to be, you have a plate for each document, okay? So a plate. Each document, okay? So j equals 1 through n. Okay, and so this, the Bernoulli will produce label, okay? Label L sub j is either a 0 or 1, depending on what we have here, okay? All right, meanwhile, okay, so this is going to be our kind of our hyper, or maybe here I'll say gamma theta is the vector used to define the Dirichlet distribution. Dirichlet distribution, okay? And this, from the Dirichlet distribution, this is going to be kind of our prior thing, we're going to get a vector theta. Okay, and there are two vectors of theta, okay? 2 theta vectors. Okay, one for class 0. Class 0 has its own theta vector, and another theta vector. Another theta vector for class 1. Okay, I guess technically these are all vectors right here. Gamma theta, gamma pi. Okay, so you got 2 theta things, right? And so depending on what label we have, we're going to either use the theta vector for class 0 or the theta vector for class 1. Okay, and so so from the theta vector, we're going to get the actual word counts. Okay, and so this uses a multinomial. Okay, so WJK is going to be the number of times word K appears in document J. Okay, so you've got K different words in your vocabulary, and it's going to say the word banana, WJK will be like the word banana appeared 5 times in document 1. Okay, the word ball appeared 6 times in document 7, or something like that. Okay, and that's what this is. And R sub J will be basically all the unique words in document J. All right, and so this is the data that we're gonna have. We're gonna have access to this data. All right, and by using this model, we're gonna try to infer back what these other parameters are. Okay. All right, so we'll take a look at this, I guess, on Wednesday. All right, and so we'll end here for today. All right, we'll see you guys on Wednesday.